Okay, so that was motion without resistance. You'll see that eventually, as we come to the topics, that a lot of the equations, or pretty much all the equations that we talk about there, is pretty much applicable to the extent the resisted motion questions, the simple harmonic motion questions, and the projectile motion questions. And so, like, being familiar with them is very important, and obviously you get more practice at doing them as you do further topics as well. So yeah, let's jump into some simple harmonic motion. Now, simple harmonic motion is defined for as it's not necessarily has to be like a physical particle, right? It's just anything that exhibits periodic motion. Now, a lot of things in the world is periodic, right? Water waves, any type of wave, pretty much sound waves, electromagnetic waves. A lot of that stuff is simple harmonic motion in the sense that it can be modeled with a sine or cosine function, or a sinusoidal function, or a linear combination of both if you want to. But the simple harmonic motion that is quite often talked about in HC is just like a physical sort of simple harmonic motion. But yeah, a lot of things in the world are simple harmonic. Engine cycles, heartbeats, a lot of things. Um, and turns out sine and cosine are really versatile in the sense that you can break down any function into them. And so that's pretty cool as well. So having a good model of sine and cos can quite often translate to being able to use that for more complex signals and things like that. But that's going off on a tangent. So here we have two models. We have x equals a cos nt plus alpha plus c, and x equals a sine nt plus beta plus c. We'll talk about each one in detail, but bit of terminology. C corresponds to the center of motion. A is the amplitude. 2 pi on n, that is the n that's attached to the t on both of them, that dictates the period of motion. The quantities nt plus alpha plus and nt plus beta are called the phase of motion. That's just talking about, and particularly the alpha and beta, what they do is they talk about what if we're modeling two events simultaneously, right? And we start one later than the other, or we start both simultaneously, or we start the second one much earlier than the first one. Obviously, they're not going to be in phase, right? Or if we're using two simple harmonic pendulums, but one's got a shorter length, right? And so even though we start them at different positions, we're going to end up with different alpha and beta. They're related to the phase of motion. So each angle, alpha or beta, is called the initial phase. So, like I said, many things exhibit repeated patterns or oscillations. So examples include heart beating, heart beatings, lungs breathing, engine motion, vibrations. Very important when you're talking about structures and things. Vibrations can, when we're talking about frequencies that sort of resonate and amplify very significantly. You have to be careful in terms of what frequencies do that, particularly for certain types of structures. Um, Waves on the beach, tides of the ocean, phases of the moon, all these things are simple harmonic. That is, they repeat in a periodic cycle, in a well-defined periodic cycle. And the mathematics behind each of these examples is extremely complicated, but each one can be based on oscillations observed in the graphs of sine and cosine functions. In the real world, when talking about oscillations, right, even suspension systems can quite often be modeled with oscillations, or to a certain extent damped oscillations, but in essence they involve sine and cosine and are built up on a basic simple harmonic motion model. So the graph of x equals sine of t and x equals cosine of t should be not cos. Cos of t is called sinusoidal. So we've got amplitude is, and again on terminology, if we graph that displacement, so x as a function of time, the height of the peaks from the center is called the amplitude. The period is the time between two peaks or two troughs, or sort of the time required to complete one full cycle. And that's the that's just a few basic terminologies. We'll come to more of them in a second. But whenever the graph of displacement x versus time t for a particular motion is sinusoidal, that motion is called simple harmonic motion, or SHM for short. And the equations are often written as, like we mentioned before, x equals a cos nt plus alpha plus t, or x equals a sine nt plus beta plus c. But like I mentioned, you can also have a linear combination of them. So x equals a cos nt plus b sine nt. Now, that is less common in at least for HSC syllabus, but effectively, if you're looking at the auxiliary angle form, the top two are equivalent to the bottom two. It's just instead of having an alpha or beta, we're talking about two separate cos and sine functions. But you can sort of combine them using auxiliary angle form and turn them into the top ones. Okay, so here when we're talking about the value, that should not point to the n, that should be pointing to the a. Sorry. So that's that one. That one's that one. Looks like Slides has done something. And C. Okay, so the value A is the amplitude, the motion because amplitude of the motion because waves move away from the center by A. So again, if this was our graph, our amplitude is just this distance here from the center to the peak. Now, if the center is shifted up or down, it's still the distance from the center to the peak, not necessarily from 0 to the peak. And so that's going to be A. So what that A does is that defines where the limits of that motion is. So if you're thinking about, say, this is a very common example, or a sort of stock standard way of explaining things. It's a block on a spring, resting on a surface, and it's moving back and forth, right? That is a very stock standard example of simple harmonic motion, and if this is our center, the two extremums are c plus a. That's our maximum in that direction, and the maximum in this direction is going to be c minus a, right? So it's going to be oscillating between c plus a and c minus a always. It's never going to exceed those bounds. That's what the a does, and that's what the c does. C, again, is center of motion. That's our middle point, and that should be the average between our lowest point and our maximum point. Okay, and n, this value n that's attached to the t, that corresponds to the period. And this formula here is very important. The period is 2 pi divided by n. And this formula is not only applicable to extension 2 simple harmonic motion. Just whenever you're graphing these sort of things, one of the first things that you should look at is what is the period. And so to figure out the period from this equation, you take n and you divide by 2 pi. So if n is 2, the period is pi. If the n is pi, the period is 2. And you just put in the respective value of n into that formula, and that should give you the period. And remember, the period is the time required to complete one full cycle, or you could also look at it as the time between two peaks or two troughs. Okay. At any time t, the quantities nt plus beta and nt plus alpha are called the phases of the motion, as their values determine the location. So pretty much the thing inside the brackets, those are called the phases of motion. Those, depending on what the time is, sort of dictate where the particle is at some point in time. Alpha and beta are called the initial phase, as they determine the initial form, or sort of if one is launched from the center and one is launched from one of the extremum, clearly those two particles are going to have different equations of motion, and that's what the alpha and beta account for. Okay, moving on. So when we start with our displacement as x equals a sine nt plus alpha, we'll drop the c for now because it doesn't really do much other than dictate where the center is. Our velocity expression, if we take the time derivative, is going to be a n cos nt plus alpha. Right? Just take the derivative with respect to t, and so the thing inside the brackets is just dependent on t with that linearly. And so taking the derivative of nt plus alpha is just n, stick that out at the front by chain rule, so we end up with a n cos nt plus alpha. So that's our velocity. From there, we can go ahead and take the time derivative again, and that gives us our acceleration, right? Remember, dx dt, second derivative, d squared x dt squared, that's going to be our acceleration. So if we take the time derivative of that, we can bring the n out the front, right? Because derivative of nt plus alpha is still n, still linearly dependent, and so by chain rule, we end up with minus an squared, and derivative of cos is sine, so sine nt plus alpha. And so that's our acceleration expression. Now, if we look carefully at our acceleration expression, we see that we've got an sine nt plus alpha with an a, right? Or we can express this as, we do a bit of rearranging, a bit of reshuffling effectively, minus n squared a sine nt plus alpha. Now, if we have a careful look at that, and we look at where have we seen that expression before? Well, we've seen that expression right here. That was our position expression, right? And so we can say that our x double dot, our acceleration, is minus n squared x. Right? And that's pretty cool because we can say that our acceleration is linearly proportional to our position, right? Because n is just a constant. So our acceleration is linearly proportional to the position. Now, we could go another path, and that is we start with our velocity expression, so we take that down there. So we have v equals an cos nt plus alpha, and if we square it, right, we get v squared equals a squared n squared cos squared nt plus alpha. Now, that looks like a bit of a mess, but the reason that's helpful is because we can use the Pythagorean identity, and we can express a squared n squared cos squared nt plus alpha as 1 minus sine squared nt plus alpha, and we've got a whole bunch of constants attached to it. So the cos squared is that, and we've got a constant of a squared and n squared attached to it, right? And so if we express that in that sense, we've got v squared equals to n squared times a squared minus a squared sine squared nt plus alpha. And so why is that useful? Well, if we look at this a squared minus a squared sine squared nt plus alpha, we see, well, where have we seen that before? That was our position function. And so we get v squared equals n squared times a squared minus x squared, right? And so that has some significance in terms of the physical sort of observation of simple harmonic motion, and we'll talk about that in a second. But those are our sort of very key distinct equations for simple harmonic motion. Obviously, the position, velocity, and acceleration sort of come from that. But acceleration, if something satisfies this equation here, that quite often means it's simple harmonic motion. If something satisfies this equation here, it means it's simple harmonic motion. Okay. And we have a similar sort of case for cos. We have a cos nt plus alpha, time derivative gives us velocity, minus an sine nt plus alpha. Second derivative with respect to time, we get x double dot equals minus an squared cos nt plus alpha. And so we get x double dot equals to minus n squared x. And squaring the velocity and so on gives us the same expressions. So it doesn't matter whether you start with sine or cos, you can end up with the same acceleration and velocity expressions in terms of position, like the relationship to position. You get, these two very useful results like we mentioned, and as we work through problems, you'll start to see patterns to understand which form sine or cosine is best to use in particular situations. But for a particle to be undergoing SHM, or simple harmonic motion, it needs to satisfy that. So that is, if you're asked to check whether a particle is undergoing simple harmonic motion, let's just say the sine or cosine function isn't very clearly built in, you could just test whether the second derivative with respect to time, that is the acceleration, is it proportional to minus n squared x. Now recall that Newton's formula for force gives us F equals ma, and so you can apply it to simple harmonic motion. You get F equals minus mn squared x. So that is, our force has to be proportional. Force has to be proportional to position, right? Because this mn squared, those are just constant, minus mn squared, those are just constants. So our force is proportional to position. If that's the case, that's a very clear example of simple harmonic motion when we're talking about springs. Springs, the more you elongate them, the harder they pull, right? And it's actually a linearly proportional relationship. And so we end up with this being a very stock standard, perfect example of simple harmonic motion. Sometimes you might see pendulum cases, but the thing with pendulums, just the regular pendulums, like these ones that go back and forth, is that it's only simple harmonic motion for very small angles theta. well, not very small, but for reasonably small angle theta. If you pass a certain point, then it becomes sort of quite bad in approximation. For simple harmonic motion is no longer a good approximation, but yeah. A very stock standard example is a block on a spring. Now, the negative sign, what it shows is that the force is directed towards the center of motion. If you, again, with the block on a spring, the further away you pull it from the center, right, the force is pulling it towards the center, not away from it. That's what the minus sign shows. Now, there are a few important results we can get from simple harmonic motion. That is, x dot equals 0 gives the magnitude of the greatest acceleration, and x double dot equals 0, i.e. at the center of motion, the speed is greatest, i.e. the velocity has its greatest or least value. It's sort of hard to describe in words, so here's a diagram. We have, at this point, right, so at acceleration 0, where the speed is the greatest, right, at this point here, so if, again, this is a particle on a, block on a spring or something, right, at the very center, the acceleration is 0, and the acceleration is greatest at the extreme points, where the speed is 0, right? So here and here, the acceleration is the greatest, but the velocity is 0. So if you think about the block on the spring case, when it approaches a maxima, it's going to have 0 velocity. When we're approaching the center, right, it's going to be going quite fast, but the acceleration is going to be 0. Why? Because the distance that the spring is compressed is 0. Because if you're right in the middle, the spring isn't compressed or expanded, and so therefore the sort of acceleration that it displays is 0. At the extremum, the acceleration of is maximum because the spring is extended as maximum. So yeah, that sort of corresponds to our physical interpretation of simple harmonic motion as well. Okay, so simple harmonic motion about the point x equals c will involve a vertical translation of a trigonometric graph. The equations of motion for simple harmonic motion about the point x equals c can be written as so. Again, the c doesn't really do much other than shift our motion to the left or right or up or down or whatever. It's just there to show that the center is no longer 0, it's at some value. So let's just say now, if this is our axes, right, rather than having the center here at the origin, if, say, we're 1 meter across and now the spring or the particle oscillates between 0 and positive 2, well then our center of motion is going to be 1. That's all it shows. So that just means that it's going to be oscillating about this point. It's going to go to 2, back to 1, 0, 1, 2, and everything in between. So how does that change our displacement, velocity, and acceleration functions? Well, our displacement function has a little plus c added to the end. Our velocity function, that's just going to get rid of the c, right? Because if we take the derivative with respect to time of constant, it's just 0. The acceleration, again, if we take the derivative, doesn't really do much to it. But when we look at the acceleration and position relationship, we need to bring the x minus c, we need to bring the c onto this side in order to have that expression as being this one. And so that's where the x minus c comes from. And so in that case, it's just used to show that because it's still linearly proportional, right? The acceleration is still linearly proportional, but it's just the minus c is there to show that where at the center is no longer 0, it's at some point c. Because if we put in x equals c, that is, if we're looking at the point at which the particle is at the center, the acceleration is going to be 0. Because, again, spring on a block example, the spring is no longer compressed or expanded or in tension, and therefore the acceleration is 0. So where x equals c, the center is that's the center of motion, sorry. A is the amplitude, 2 pi on n is the period, and alpha on n is the phase shift. So, let's do an example. This one is, I think, from 2022. 2022, I believe. So this is just an example of modeling with simple harmonic motion. It's not really too hard of a question in the sense that it's not something that involves a lot of heavy calculation. It's just something that involves modeling. But that's a really important skill to have, obviously, in the real world. If you're modeling something, sort of modeling comes first, and then your sort of analysis or the details. But modeling something accurately is very important. So the diagram shows two pistons of a single piston in the cylinder chamber of a motorcycle. The piston moves vertically in simple harmonic motion between the maximum of 0.17 meters and a minimum height of 0.05 meters. The mass of the piston is 0.8 kilograms, and the piston completes 40 cycles per second. That, remember, 40 cycles per second, that corresponds to a frequency, but the frequency can be related to the period. What is the resultant force on the piston in newtons that produces the maximum acceleration in the piston? Give your answer correct to the nearest newton. Okay, so first step is to come up with an expression for position, right? Is to come up with an expression for acceleration, or we could start from position and then get to acceleration. But if we can jump straight to acceleration, that's probably a bit faster. So let's look at what's happening in this case. What's our center of motion? Well, our center of motion is going to be the average between our minimum and our maximum. So our minimum is 0.17, and our minimum is 0.05 over 2. If you put that in the calculator, that is 0.11. That's our center. That's going to be somewhere about here-ish, I think. 0.11 meters. That's our center. And what does that mean in terms of our amplitude? Well, our amplitude is just going to be the distance from the center to either the minimum or the maximum. And so we end up with the amplitude is going to be, say, 0.17. We're going to take the maximum minus 0.11. So our amplitude is going to be 0.06 meters, right? And obviously that's going to be important in terms of when we're talking about acceleration equation and so on. Next thing to look at is the period. We're given the frequency is 40 cycles per second, or 40 hertz. So 40 cycles per second means that we're doing 40 sort of up and down motions each second, right? And so that means the time required for each sort of cycle is 1 on 40 seconds, or a 40th of a second, because if we have a 40th of a second and we can do 40 of those, that means, if we have each cycle takes a 40th of a second and we have 40 of those cycles, that's just going to mean 1 second. And therefore the period of each one must be 1/40th of a second, or in decimal form, 0.025 seconds. Okay, so that gives us the period. Why does that help with developing our equation? Well, that's going to help us get n. Because remember, 2 pi on n is the period, and hence we can go the other way and say that n is 2 pi over the period. And so we have 2 pi divided by 0.025. So that gives us 80 pi. Oops. 80 pi. And from there, what do? Well, we've got n, right? We've got the center of motion. Then let's try and fill in this equation. X double dot equals minus n squared x minus c. We have the details required, so we can say that's equal to minus 80 pi squared times x minus 0.11. And so our acceleration function becomes minus 80 squared, which is, let me do 80 squared, that's what, 6,400? 6,400 pi squared times x minus 0.11. Okay? Now, the question's asking for when the maximum acceleration occurs, the force when the maximum acceleration occurs. Clearly, maximum acceleration is going to correspond to the maximum force because F equals ma. And so when does the maximum acceleration occur? Remember, maximum acceleration occurs at one of the extrema. Doesn't matter whether it's the minimum or the maximum. Either way, the maximum acceleration occurs when it's furthest from the center. And so let's take the maximum value. So x equals 0.17, for example. Implies that x double dot, so if x equals 0.17, we get minus 6,400 pi squared times 0.17 minus 0.11. And what does that give us? So 6,400 times pi squared times 0.17 minus 0.11. That gives us 3789.928. So 37899.928 meters per second squared. Again, the units, right? Units for acceleration, if we're dealing in SI units, is going to be meters per second squared. It's just going to be our unit for distance over our unit for time squared. So that means that our acceleration maximum is going to be about 3789.928 meters per second squared. And you can leave it in exact form if you'd like to. In this case, probably okay to round it because we're looking at sort of in mechanics, I would say rounding is fairly reasonable. Try and leave it in exact form if you can, but they shouldn't be too critical of rounding because it is mechanics in the end. Anyway, we have F equals ma, right? For our force, because we're asked for the force of the maximum acceleration, not just the maximum acceleration. There is a negative sign here, but we're interested in just the I guess they're just purely interested in the magnitude of the force, although the force is clearly going to be directed towards the center of motion, just with any simple harmonic motion question. So we get 0.8 kilograms was the mass of the piston times the acceleration, which is 3789.928. And so that means that our force is going to be approximately 0.8 times 3789.928, 3031 or 3031.942 newtons. That's our force. I'm sorry, 3 drop to 2. Yeah, 3 1. So our force is approximately 3032 newtons. It says the nearest newton, so we're going to give it to the nearest newton, so 3032 newtons. That's our maximum force. Now, in terms of force, usually you want to specify direction, and the direction for simple harmonic motion is quite often just towards the center of motion. Okay, next question. The point P is 4 meters to the right of the origin. How are we doing for time? Okay. Because we are running sort of short on time, what we'll do is we'll do this one, and then we'll potentially, we'll see how we go with this one. So the point is 4 meters to the right of the origin on O on a straight line. Particle is released from rest at P and moves along the straight line in simple harmonic motion about O with period 8 pi seconds. After 2 pi seconds, another particle is released from rest at P, also moves along the straight line in simple harmonic motion about O with period 8 pi. Find when and where two particles first collide. So we're asked to find when, which is a time question, and where, which is a position question. Okay, now this is a bit of a tricky question, and so one of the very helpful things to do is draw a diagram. So if we draw a diagram, this is our line about which the oscillation occurs. This is O, this is the center of motion. This is P, and this is, we're going to call it Q. This is our sort of other extreme. The question says, particles released from rest at P and moves along the straight line in simple harmonic motion. So because it's released from rest at P, about O, sorry. So because it's released from rest at P, the particle is here, right? And it's in simple harmonic motion about point O. And that means that it's going to take half the time to get here, right? And then half the time to get here. It says that the period of the particle is 8 pi, right? And so if the period of the particle is 8 pi, that means it's going to take 4 pi for sort of one all the way this way, and then 4 pi for back, right? So that means it's going to take 2 pi to get to the center, and 2 pi to get to this extreme value. Right? So after that, 4 pi seconds has elapsed. Now this is, again, a bit tricky to see, but hopefully you can follow along with the logic. Then the question says that after 2 pi seconds, that is, when the particle is at P, right? When the particle is at O, after 2 pi seconds, another particle is released from rest at P, and also moves along the straight line in simple harmonic motion about O with period 8 pi seconds. That is, so you got two particles, identical setup, so again, spring and block system, identical spring, identical block, and they're in simple harmonic motion. The only thing that's different about them is that they're released at different times. We're asked to find when the two particles collide and where. There are two approaches to this question. One is to try and come up with equations of motion for both and try and look at what time it collides by equating them both. That's a perfectly valid solution, but there is a bit more of a clever way to do it. Sometimes in an exam situation, now I always emphasize this, sometimes in an exam situation you might not be able to see that, the sort of cleverer way. So if you've got the time to do so, brute force it, do it. But sometimes, look for a cleverer way, and that could save you potentially 10 minutes worth of working. Okay, so we got 0, so from P to O is 2 pi seconds, O to Q is also 2 pi seconds. So by the time this particle, the red particle is, let's just say the starting one, the first particle, by the time it's at O, the second particle is released from P. So by the time the second particle arrives at O, the first particle's already arrived at Q. Right? Maybe I'll use a different color for that. Let's use yellow. So by the time the first particle is at Q, the second particle is at O, right? But the second particle is still moving this way. The first particle is still moving this way. And so they meet at the center, right? Because of symmetries, they meet at the center of the time period, not necessarily at the center of not necessarily at the center of motion, right? In terms of the physical space, but center of the time periods. That means that they meet on the journey back of the Q particle and on the journey up of the particle that was at O. And so that means that because it takes 2 pi seconds to get here, halfway between them is going to be pi. So we get T equals to the first 2 pi, that is the 2 pi before the second particle was even released, plus the 2 pi at which point the second particle was at O, first particle was at Q, plus the time at which they meet, or like the sort of the midpoint time between the O and Q at which they meet is pi. And so the maybe I won't use capital T, maybe I'll use little t. The point in time in which they collide is 5 pi seconds. Again, that might be a bit tricky to see in an exam situation or to reason that out. Try and explain it to yourself as well, because some of these questions, the logic behind them is a bit tricky, but try and sort of look through or imagine the situation. That I personally feel like it really helps. So you have 2 pi, suddenly the second particle gets released, this one gets to Q, this one gets to O, and then on the way back, or on the way up for the second particle, on the way back for the first particle, they meet in the middle, which is pi, so t equals 5 pi seconds. Brute force method also works, by the way. Okay. So that answers the when question. We're now interested in the where question. That is where the two particles first collide. Because we're interested in the where question, we need to come up with an equation of motion for at least one of the particles. And I believe that the first one is probably going to be easier because we're not going to have to deal with some sort of phase shift. So we can say x equals to, what's the amplitude? Well, the amplitude is going to be, look back at the question, amplitude is going to be 4 meters because the point P is 4 meters from the origin, and we're centered about the origin, and so the amplitude is going to be 4. We can use a cos or sine, but because we're starting at the extremum, right? Sine starts at the origin, cos starts at 1, right? Because we're starting at the extremum, we're going to use cos because it's going to start at the higher point. Cos nt. Now, n in this case is dependent on the period. But we know that the period, t equals 2 pi on n, and so n is going to be 2 pi over the period, and so we end up with 2 pi divided by a period of 8 pi. So we get 1/4. And so we can say that x equals 1/4 t. That's our n. So nt. And now t is 5 pi, because that's the point in time which they collide, like we reasoned before. So we get x equals 4 cos 5 pi on 4t. Sorry, 5 pi on 4, if we sub it in for t. And now if we evaluate that, cos 5 pi on 4 is minus 1/2, right? And so we get 4 times, now minus 1/2, we can say minus √2 on 2, right? Just by rationalizing the denominator. And so if that cancels, we get x equals to minus 2√2 meters. That's the point, that's the position at which they collide at t equals 5 pi. At t equals 5 pi, x equals to that. Again, not necessarily the center of O and Q, but it is the center in terms of time. So you have to be careful to differentiate between time and position and centers, because it's not necessarily symmetric about, it is symmetric about position, but not in terms of O and Q, or like in terms of how much time it requires, but it is symmetric in terms of time. Okay, we'll jump over this one just for the interest of time. This one shouldn't take too long. So we have a particle is moving along the x-axis, and in simple harmonic motion, the displacement of the particle is x meters and velocity is v meters per second. Parabola below shows the function of x. Function of x. So v squared plotted against x. Part 1 asks for what values of x is the particle at rest. Not a trick question, very easy. Well, if the particle is at rest, v equals 0, v squared must therefore also be equal to 0. And when's that the case? At x equals 3 and x equals 7. So part 1, the answers are x equals 3, x equals 7. Okay. From there, we have... So from there, we have what is the maximum speed of the particle? Again, not a trick question, not hard question. It's just v squared is 11. So if v squared is 11, maximum speed must be √11 meters per second. Part 3 is where it becomes a bit more interesting. The velocity v of the particle is given by the equation v squared equals minus n squared, a squared minus x minus c squared. That's the equation that we derived before. We're asked for what n, a, and c are. And that's worth 3 marks. So first, we're going to look at what the center of motion is. So if the particle is at rest at 3 and 7, that means those are our extremum, right? Those are our extreme points. So the center must be the average of them. So 3 plus 7 is 10, divided by 2 is 5. So we know that the center, C, must be 5. Right? Easy as that. And then from there, we're asked to find what what A and N is. A is just corresponding to the amplitude. So if the center is 5, our extremes are 7 and 3, amplitude must be 2, right? Because the distance from 5 to 7 is 2, and the distance from 5 to 3 is also 2. What's the value of A? What's the value of N? This is where things get a bit more interesting. This is when we're going to have to use potentially like the actual formula itself. So we're going to say V squared equals to N squared times 4 minus X minus 5 squared, right? We're going to plug in V squared equals 11, right? That occurs at the center at X equals 5. So the second term in the brackets disappears. N squared times 4 is equal to 11. So you get N squared equals to 11 over 4. And so N must be root 11 on 2. And that's our N. So we get A equals 2, C equals 5, N equals root 11 on 2. Easy as that. I'll also skip over this one. The solutions are in the slides if you're interested for this multiple choice question. The reason I put this here is also a bit of a warning. Sometimes multiple choice questions can seem deceptively simple. Like for 1 mark, you might not expect that amount of work, but as you can see, it does involve a bit of work to get the answer out. Sometimes trial and error does work, but not always.